I'm starting. Okay. Hey everyone, my name is Yan Kai Chen, and I will be your host for tonight. And I thought something we could start with is just if you could put down the chat where you guys are viewing from, that'll be great. Otherwise, I thought I'll start off by talking about what Space Generation Auckland is. So we're actually a club at the University of Auckland. And so we aim to foster a student space community here in Auckland, improve the community's space knowledge, as well as the awareness of the international space sector, and connects students with opportunities in the sector. And some of the stuff we've done so far are mostly talks. So we had a talk on space sustainability where we looked at deorbiting technology. We recently had someone from Rocket Lab talk about her journey to the space sector. And tonight we'll be looking at space biology and health. And we have a couple other talks planned out. And otherwise, we have movie nights and game nights as well, visits to facility that we plan to do after lockdown ends. Otherwise, I thought I'll briefly talk for our overseas viewers. I thought I'll just let you guys know where New Zealand is, in case you don't know. Auckland is in that smaller circle, and our speaker is in Australia, Sydney. And just a bit of housekeeping to keep in mind is that, so if you have questions, put your questions in the chat, and we will indicate to you when you can ask your questions. And so when asked to, you can unmute your mic and ask your questions directly, and feel free to introduce yourself along the way. And otherwise, today our speaker is Dr. Joshua Cho. Joshua, he did his bachelor, honors, and PhD at the University of Technology, Sydney. He did postdoctoral research at Musashino University in Japan. He was a research fellow at the Harvard School of Dental Medicine. He is now back in UTS, where he is a senior lecturer and the director for biomedical engineering and medical science. He's also part of the Space Medicine and Life Science Technical Advisory Committee at the Australian Space Agency. Welcome, Joshua. It's our pleasure to have you here tonight.
Thank you, thank you. All right, my turn to share my screen. Okay, so can everyone see this?
I can. Yeah.
Okay, good. All right, good evening, everyone. Thank you for your kind invitation to speak with everyone and share with you, what we're doing in terms of our research, in terms of, our development over here in Australia, and how we're integrating and connecting with the rest of the world. It's a real pleasure to be able to speak to your group at University of Auckland. People don't know this. I actually lived in New Zealand in Auckland for 3 years. I used to play at the University of Auckland when I was a kid.
Personally.
So yeah, so it's a real pleasure to be able to connect through virtually. So tonight I'm going to share with you about my research on the human element of space. How are we going to survive and thrive in space? And I think that's a very critical topic, given that now we have much bigger ambition and aspiration to go longer and deeper into space. The human element is obviously the most critical aspect of that. But I think there has been quite a lack of research in that area, in this area particularly, and now we're trying to do a little bit of catch up. So tonight I'm going to share with you a little bit of background and perspective, and what are things that we're doing, and more importantly, opportunities for you, whether you're a researcher or student, to get involved. It took me a while to really cut down on what I can share with you, given the time limit, as we actually do quite a lot, and of course the depths of what I can share. So I've kept things quite general, or at least in a way that's easily absorbed. So happy if you have any questions, look forward to answering them towards the end. Okay, so again, this is just a quick rundown. Yinkai has already done a great job of introducing me, so I won't spend too long. This is just really to show that I can speak to what I'm saying. So my lab here at UTS, we focus a lot on different aspects of I guess biomedical engineering. I'm a cell biologist by trade, by training. But I'm fortunate to be in the biomedical engineering school where we have a lot of talented engineers to help us build the tools, because when you're talking about biology, a lot of the tools or technology doesn't exist, and we actually have to build them from scratch to be able to do this type of or this level of research. So you can see we actually do a lot of different things, and that's why it was a bit difficult to narrow down to what would be of interest to everyone. So I like to start off my talk with putting things into perspective. Living and exploring space has always been part of our culture, and it's obviously depicted very well in lots of presentations and movies. So these are kind of my personal favorites. Everyone has different, and I think it's that inspiration and hope that of space, that and also the mystery behind it that really attracts us to it. So we're not unfamiliar to space, and more importantly, the challenges and the danger of space, because ultimately that the environment is considered an extreme environment, and it wasn't meant for human physiology to be in there for too long. So that kind of put things into context of the various and different levels of challenges of space. So as everyone know, we have now in our site different missions being planned to go to the moon, to go to Mars. Everyone has different ideas about how we're going to do that. Obviously, from a technical point of view, we can be able to do that. But the biggest question, or the ultimate question, is how are we going to survive the journey, and also how we're going to survive the planet when we get to the planet that we want to go. So there's really two different aspects and elements that we need to consider and to be able to address before we can actually make these real long-term and deeper voyages to colonize other planets, essentially. So everyone is very familiar with the Artemis Project, and that is really going to the moon and then establishing a base that will ultimately support the mission to Mars. So Australia is part of that, I guess part of that accord in supporting NASA with that mission. So there's a lot of things that needs to be done, and to be able to support that kind of mission. So you can also see that as in terms of space health and in terms of space health, we still have a lot to address, because there are a lot of conditions that manifest as the human body become exposed to the environments of space. And of course, a lot of people have been looking at developing medical treatments, emergency, and also 3D printing. That is a really big one and popular because of obviously we can't bring everything with us. So if we can 3D print them, that will obviously be much better. Because in terms of if there was a medical emergency on the ISS, I think the extraction time is about 24 hours. If it was on the moon, it's about 7 days. And then after the moon, there is pretty much no emergency extraction. So anyone that's going on that kind of mission will be on their own. So we really have to equip them with the capability and the technology and the know-how to be able to survive if and should anything occur during that voyage. So I don't know about you guys. You're obviously in this club because you might, at some point in your lifetime, you had a dream about space, like myself. Visiting the stars one day, and that was a dream. But these days, it's becoming more and more of a reality. And I think what we're all looking forward to is to really live, whether it be short term or long term, in space and beyond. So this really brings me to the topic of tonight, of space biology. So what is space biology? What's involved about space biology? And what do we do actually in space biology? And really, it really comes down to, how does, the space environment and mainly the effects of gravity, there are other things, but how gravity shapes life and how we can improve life on Earth using the knowledge we gain from space. So space biology is really to support enabling explorations of other planets or being in space, obviously making new discoveries, and more importantly, improving life on Earth. So I think like most space advancement and technology, there's that duality of that conversion of that technology being applicable to life on Earth. So again, I'd like to put things into perspectives about gravity shaping life on Earth and in space. So gravity affects the body starting from the cellular level all the way to the tissue organ level and obviously to the organism level. So if we all know, it has significant impact on the organism level. So if you kind of go backwards, you're going back into the tissue and the cellular level. And so it's all interconnected. And that's what space biology is really about, is, how do we look at from the cellular level, tissue level, and organism level to be able to understand what is happening and its effect. We also have to understand that, throughout human history, everything has changed. The climate has changed, geography has changed, people have changed, but gravity has remained quite constant. It's probably the only one thing that hasn't changed. So pretty much everything on Earth has a memory or recollection of how gravity defines it. But when you go into space, there is no, there's nothing on Earth that has that memory of being in that kind of microgravity environment. So that's why, because it's not accustomed to it, it will react quite aggressively to it. So let's start off at the systems level. We all understand there is quite a lot of significant medical challenges with space flight, because space flights can last from days to months, and then probably now even years. So there's obviously different types of medical risk profile associated with it, but it's pretty common sense that the longer you stay out in space, the more exposure, the bigger the impact. So this is really, just summarizes some of those medical challenges, both, exposure, short-term and long-term exposures. And you can see that there are a lot of factors, and you can see those immediate responses to microgravity and also the long-term one. Obviously, this is, again, going back to what I was saying, the longer you stay out there, the more exposure you have, the more impact you're susceptible to. So like I said, being in space doesn't mean the only thing is microgravity that's affecting you. There's obviously radiation, cosmic rays, magnetic fields, and radioactive environment of the planet. So there's a lot of factors. And that's why I said, space wasn't intended for humans. But now that we have those ambitions, how do we actually protect ourselves to be in those type of environment? So, like I said before, there is no memory of living organisms on Earth that has been exposed to microgravity. So microgravity, as everyone knows, you see that picture of people floating around. It's obviously, it means there is lack of gravity. Lots of people say zero gravity, but there's still a little bit of it. So the term microgravity is probably more of the right term. So one way to look at it is microgravity, which means the lack of gravity, but you can also think of it the other way from a physics point of view, is that you are exposed to very, very small amount of gravitational force. So that interpretation can mean a little bit different for different people. So that's where the major interest is right now, is microgravity research into how we can use or leverage microgravity research for biomedical research, fundamental science, and of course all these is to support space exploration. So the reason why people are interested in it is because it depicts a lot of the aging diseases down here on Earth. You can see from this list, osteoporosis, muscular dystrophy, cancer, obesity, and so on, bed rest, long-term bed rest, spinal cord injury, aging in both male and female. So it really induces and accelerates the aging process. And that's what gives it its unique, I guess, environment, because we can study accelerated aging, so to speak, under microgravity. And that actually helps researchers quite a bit. So this is kind of where I'm going to talk more about is, I discuss about the, more, systems level, tissue level, and now we're going to really, go straight into, the biological and cellular level. So one of the main, or everyone is aware of, the main response to microgravity is the loss of bone and muscle, right? Like everyone knows, when you go up there for too long, you come back, you lose a lot of muscle, you lose a lot of bone. And that's because, your muscle and your bone relies on mechanical loading. And this is exactly, you needing to go to the gym. That's why doctors say you have to exercise to maintain certain fitness. Is that the importance of that mechanical loading on your body's homeostasis, because that mechanical loading actually induces a lot of cellular and intracellular processes that governs your not only tissue growth, but your overall all your other organs and its interaction. So, we all know, as I mentioned, in microgravity, there's significant loss of bone, and that's a big problem because it's basically a framework. If we lose so much bone on the trip to, let's say, Mars, by the time we get to Mars, if we've lost significant amount of bone, we won't be able to walk, let alone explore anything. We'll just be a pile of jelly. So, while other organs, you can have a certain level, I suppose, of, damages, bone is something that you really can't if you want to be able to walk, work, walk around and whatnot. So, you can see that, in terms of space flight, you lose about, let's just even lowball it, 1% per month. So that is already quite significant. So this has been, well, I guess for a while, for the last, I guess, decade or more, has been a primary focus for people, the likes of NASA, is how do we, limit this, or at least slow down this effect in terms of the skeletal bone loss. So for us to really understand, why these things are happening to the human body, we have to understand, some basic concepts that is already being part of our life. It's just we haven't really put a name tag to it. So this, I mean, if you think about it in life, mechanical stimulation, like going to the gym, cycling, those are mechanical stimulation. Even if you think about braces, you're applying forces to the teeth for it to move. Most people enjoy massages, especially, middle-aged men like myself. I enjoy massages, and that is obviously some form of mechanical loading on your body to help relieve stress. And of course, females, skincare, those electrical stimulation on the muscles help stimulate those at the cellular level for those regenerations to happen. So mechanical loading and its importance and how we live healthy, it has always been around. It's just that now we've actually put a term to it and calling it mechanobiology. So if you put mechanobiology, importance, and space together, you bump up a new word called space mechanobiology. And I like to say cells have feelings too. For a very long time, people treat cells as just, these cells that just kind of randomly, do their stuff, but they're actually much more sophisticated, obviously, to be able to maintain our physiology. So really, the mechanobiology is obviously the principles of, combining mechanical forces with the biology. And if you have a look at this graph, you think about, your brain, that's really, really soft. And then kind of that goes into lung, liver, your muscle, and then to bone. So your body and different tissues and organs have different types of stiffness. And this is very important because cells behave differently on different type of stiffness. And that sets the underlying mechanisms of what mechanobiology is. So you can have the same cell, for example, over here, but on different hardness substrate, they will react differently. And that is no different than if I were to if I ask you to try to stand on water, on a concrete pavement, or on sand, how you walk and interact on those surfaces will of course be very different because you're trying to compensate for it. So if we look in the context of bone, and really understand, what's happening. So bone, we all understand, as part of the aging process, in particularly in female, osteoporosis is a real big issue. It's a silent disease that you don't really know until you have a fall or you go and get a check. And basically osteoporosis is an imbalance of, bone building. And so this is a matrix showing a normal healthy bone. And this is osteoporosis where you have a loss of bone density. So it was really only, I would say, about 10 years ago that people in the bone field really started to identify a cell known as osteocytes that are critical and crucial for the proper function of bones and other organs. Because for a very long time, it was really just about osteoblast, which is your bone building cell, and then osteoclast, which is your bone resorption cells, basically build and destroy. Osteocytes for a very, very long time was disregarded. Some scientists even said it doesn't have a function, it's just there. And I don't understand how people would think that, because 90% of your bone cell is actually osteocytes. And for someone to really come and say, it has no function is actually quite preposterous. So anyway, long story short, people realize that, osteocytes is actually the main cell. Because if you think about it, osteoblast build, osteoclast destroy. Osteocyte is basically the manager. If you think about it in the context of building a building, you have builders and you have people who destroy. Osteocytes are basically your managers. They tell the cells how much to build and how much to destroy. So if you have an imbalance, it means it's giving the wrong order. So if you put it that way, it's really important to understand how osteocytes give those commands, because it dictates how much gets built and how much gets destroyed. So really, the focus and how osteocytes came about was really the discovery of sclerostin. It was first described in 2001, and it was really this gentleman over here. You can see there is significant bone outgrowth in the forehead. And they didn't understand why. It was just really thick. And after doing more deeper studies into it, they realized that it's actually secreting more sclerostin, which inhibits osteoblasts, thus inhibiting bone formation. So during my time at Harvard, and you saw before, I was in the School of Dental Medicine. You're probably wondering why I'm not a dentist. It's because the School of Dental Medicine has the world's best bone researchers, because dental and bone is, I guess, connected in one way. So we were part of that project working with NASA and Amgen in characterizing the sclerostin antibody that was jetted off into space. Basically, how that works is that it blocks that signaling pathway. And what that means is that it's basically tricking the body into thinking that you're exercising, whereas you're really not. So you're having that mechanical loading signal, but you're in space and there is no mechanical loading. So what came down from the result was actually quite striking. And that they put it into the osteoporotic model, and you can see that there is significant. Not only did we not lose bone, we actually gained more bone while being in space, and that's really unheard of. So I like to use that as a classical example of how we can leverage space into developing something of impact down here on Earth, because I think it was only 3 years ago, the FDA approved that sclerostin antibody as a new treatment for osteoporosis. And again, this shows how we are able to leverage that environment, understanding the biology and developing countermeasures. So now you have a drug that the astronauts take while being in space, and then a drug that can be used or applied for osteoporotic patients down here on Earth. So microgravity, how do you actually induce microgravity on Earth? Because let's face it, we can't possibly do every single experiment on the ISS. That just, well, I wish we all had that kind of money and ability, but that's just not possible. So there is a number of different ways to be able to do this type of studies down here on Earth. So I guess the most one that everyone's kind of heard of is parabolic flight and drop towers. But the problem with that is very small exposure to microgravity. Drop towers, you're talking about, I don't know, half a second, let's say 3 seconds at best. Parabolic flights, about 4 to 5 minutes. Similarly with neutral buoyancy, magnetic levitation, these are all short-term exposure because you can't do it for long-term. And for those people who do biology study, you cannot possibly induce any effect within a few seconds or even within a few minutes. You need time, you need hours, you need days, you need months to be able to see those changes. Just like if a human were to go into the ISS, he's not going to suddenly pop his eyeballs out. So it takes time to develop those conditions. So, for an astronaut, it's been recorded that it takes about 48 to 72 hours before they start to develop or show those type of side effects or symptoms physically. So it does take time. So that brings us to the random positioning machine. So random positioning machine is basically, if you really think about it, it just rotates around. So how it works is that it accelerates at a certain speed and the XY to compensate for the Z. And you can see there are different versions of the RPM over the years developed by other people. These guys are pretty extreme in that they put the whole incubator into it. And I guess globally, the most common or most popular one is the Airbus 2.0. So people have been able to access this and use it for different types of microgravity study. So it is actually really important to be able to have access to these technology because we can't, like I said, we can't do everything in space. So what we can do is to optimize these researchers so that when it does go into actual microgravity, we kind of at least have an idea or guesstimate of what's going to happen. So fortunately, and I have to take this moment because my company has developed an RPM dedicated for biology and pharmaceutics. We recently bought out the Airbus portfolio. So the Airbus RPM is no longer on the market because we bought it out. So essentially, we're the only people providing a more updated version of the RPM. And you can see here it fits nicely in the incubator, and it's the only RPM that has been tested under radiation. So it was really to cater for the question of these things that we see in space is a result of microgravity, is a result of radiation, or is it actually a dual results of having both? So those are, to me, those are fundamental questions, but no one has answers for them. So that's why we were keen to be able to develop an RPM that can be used for microgravity and also look at radiation. So we have these installed in government facilities because they're the only people that have, I guess, access to radiation that can mimic the radiation exposure in space to conduct this level of research. So let's get into the research. And because we have done a lot of different types of diseases, cell types and whatnot, today I wanted to share with you is about cancer and specifically breast cancer. And the reason for that is cancer is highly mechanosensitive. So if you recall just a few minutes ago, I said osteocytes and we all know bone respond aggressively to microgravity, and that's because osteocyte is the most mechanosensitive cell in the body, followed by closely with cancer cells. That's what makes it unique, because if they're so mechanosensitive, what happens when we expose cancers to microgravity? That was a fun question I had in mind when we built the RPM. I never knew that we will continue this research, publish a lot of papers, and get funding for it. because it's just absolutely interesting. So you can see in a static condition, your breast cancer over, I don't know, 20 hours, they, they see the attach fine, they expand, they connect, they do what they were supposed to do. But once they're in the RPM, you can see that they start to change morphology over time and start to clump together. Now that clumping together, I guess it's survival by numbers. If you're on a I guess on a waterbed with a lot of people on it, you're going to grab onto the person next to you so that you don't fall. I think it's pretty logical, and I think that's why the cancers are clumping together, because they're trying also to survive as well. So what was really important for us was, okay, so we see these things, these morphological changes in cancer, and they came off. A lot of them came off, and we thought, okay, maybe they die. What we found out was that they actually didn't die. They're actually still alive. It's just, I guess they lost their grip and they floated away. So we actually took those cells and replated them and see, okay, do they die eventually, or what happens? So very interesting. If you remember what I just said, it takes 72 hours for astronauts to adapt to space. Similarly, for cancer, it takes 72 hours for them to readapt to gravity. You can see over here in this image, after 72 hours, they regain their full function and capabilities. And, it was very interesting because they are capable of readapting. So, the research has now turned into, okay, so if these cancer cells has been in that environment, does it have, memories of it being in microgravity? And if it does, can it compensate for it? If we keep exposing them to microgravity, does it develop some form of survival mechanism to readapt to microgravity? So that research is taking place. We're getting interesting results, but unfortunately, I can't share that with you at this point. So then we looked at the migration of breast cancer, because breast cancer migration is very important because that shows their aggressiveness. And we did a scratch test. So basically, it was basically full of cancer cells. We use a tip and scratch it, and we expose it to microgravity and also control. So you can see in the control group that the cancer cell do proliferate and try to recover and fill this up. But in microgravity, it is much statistically slower in terms of migration, if at all. So we do see that it does limit their migration and thus their aggressiveness phenotype under microgravity. So a lot of people ask me, so what do you want to do, Josh? You want to send a bunch of cancer patients into space, and that's really not it. So very similar, taking the same strategy as the bone case, so the sclerostin, using it to understand which pathway or which receptors is responsible for these sensations. We did the same with the breast cancer. So we, screen, because these days we can do that, is high throughput screening. We screen basically all the drug targets in existence right now for breast cancer and see which one is actually responsive to microgravity. Funny enough, three of them, three major ones really popped out. So we've identified these three, and it's really interesting that these three, because this has got to do with their survival and function, these three drug targets. So, this is just a demonstration and kind of a proof of concept, if you want, of how we can use microgravity, the environment of space, to really identify things that would never could have been identified. Because these three targets, even though they're drug targets, they have never been linked to mechanotransduction, mechanobiology, or anything. If anything, it was associated with diabetes or some other pathway. There's never been a link to it. So this demonstrates that we've used microgravity to make that connection between breast cancer drug targets and mechanotransduction pathways. And it's quite exciting, and we're trying to look further into this and develop other type of strategies for breast cancer therapy. So like I always tell people, I'm not trying to preach that we're going to find a magic bullet to cure cancer or anything like that. It's more about how can we improve the efficiency of current therapies. If we can use this strategy to improve by 10-20%, that to me is already a win. I think that would be super awesome. So like I said, we've done a lot of different types of studies. Because of time, I can't share everything with you guys. But one of the more recent one and published only a week or two ago is brain tumor, glioblastoma. That was really interesting. Again, one of the big problems with glioblastoma, which is brain cancer, is because you have these blood-brain barriers that prevents chemotherapy from accessing the tumor in the brain. So what we've actually done is put it under microgravity to open up the blood-brain barrier so that more chemotherapy drugs can reach the GBM. So we've actually been able to do that. And now we've identifying the pathways of actually opening the blood-brain barrier. So the idea is that we can control how long it opens and how much it opens so that effective concentrations of chemotherapy can reach the GBM. Irrespective of that, we use 3D ball printing technology to recreate the GBM environment. So this is just under normal gravity. And you can see under microgravity, that cluster of brain tumors have been significantly decreased. So that is interesting because at least we know that GBMs are susceptible to the effects of microgravity, and more importantly, the blood-brain barrier is able to open up so that more therapeutic drugs can come out. And so I obviously need to acknowledge the Charlie Teo Foundation for supporting this project. So right now I'll talk a little bit about space health and making that link. So everything I kind of talked to you about is really about the biology, the cellular level type of thing. But how do you translate that into more of a, I guess, applicable level? So in our lab, in our research group, we also do a lot. And like I mentioned, we have a lot of engineers. So we are developing different tools to be able to support the health aspect. So for example, we've developed different space health suit. We have an analog mission down in Brazil next year with the Canadian Space Agency, Brazilian, and NASA, and obviously Australia. We were able to, through our satellites, we were able to take a picture of the analog environment. And also yesterday, we were able to develop, finalize, and test, actually, test is the right word, test with Amazon, a health data analytics platform in which we're able to monitor different medical signals, biomarkers from the analog contestants, I guess. And Rowena, she is here today. She's our space doctor who will be looking after those contestants and looking at how their health biomarkers change under different activities and throughout the analog missions. Also, we're deep in talk with Axiom Space in between myself and them to start recruiting astronauts and develop astronauts training program here in Australia. And everyone knows Axiom is building the first private space station to offer people to experience space, but also more importantly, to do research in space. So we are working with them to develop a suite of whether it be training program or health and microgravity research capabilities so that we can really push that boundary. Because like I said, right now, microgravity research is still limited because of obviously time, access, and of course, funding as well. So what we want to do is see how we can democratize it so that more research can be done so that we understand more about our human body and really make that translation between space technology and also human terrestrial healthcare. So, a lot of people also ask, it's all great and dandy, it's all cool, you're doing all this biology thing. So how does it translate into real life? What are some of the real world applications? So if you really think about it, bioreactors, this, I don't know, 15, 20 years ago, it was like, whoa, amazing. And now bioreactors are just part of life, part of pharmaceutical manufacturing. There are big tanks that just go through hundreds of liters each day, creating, mediums, cytokines, and whatnot in these bioreactors. So if you think about it, RPM or microgravity research is no different than a bioreactor. It's essentially rotating in 3D rather than pumping fluids through it. So I see that there's a lot of potential as some form of bioreactors in which we can create or manufacture a lot of pharmaceutics and cytokines. And of course, more recently, I've come to enjoy float therapy, where they say it's simulating that kind of microgravity environment, that flotation type of feeling. To be honest, when I only started it, because when I did all this cancer research, it generated a bit of media attention. I think 3 ladies who had cancer came to me and asked me about float therapy. They went away and did float therapy for 6 months, and either their cancer shrunk or completely disappeared. And their doctors could not explain why. Obviously, take that with a grain of salt, because that is not very scientific, but it just got me curious about float therapy. So I tried it, and it's absolutely, I can understand why it would. It's absolutely amazing. So, there are things that is translatable. And right now we are working with float therapy providers to see if we can get more data sets, to see if we can put the science behind it. And then of course, enhancing regeneration. This is something I didn't really talk about tonight, but it's something that I would like to, I guess, finish off by teasing everybody, because if you think about it, long-term exposure to microgravity has negative effect, and everyone talks about the negative effect, but no one talks about the positive effect because they think there isn't any. But what we have found is that their short exposure has positive effect, and that really, what that means is, those, I don't know, at least, there are those old people who swim in ice water and during winter, and they have, boost their immune system and whatnot. So if you think about it that way, like I said, space is an extreme environment. So it actually pushes your body and your cells to try to compensate for it. So in essence, it's stimulating regeneration. If you go too long, obviously the cells give up, and then you start to have these negative effects. But short exposure can have positive effects. And we've actually have data, which I can't really share, and that we can generate these type of, I guess, pharmaceutics and produce these type of signaling molecules to stimulate regeneration, which is really exciting. So if you think about those people who are doing those suborbital flights, paying $250,000, if you can add value to them and say, hey, not only are you going to do that, you're also going to, have improved your health. I think that would be very marketable, so to speak. And of course, like I said, the tools and the technology that's been developed in parallel to support this type of research has a lot of implications for biomedical research down here on Earth. So I just also want to, share some opportunities, because healthcare is obviously universal, and there are a lot of opportunities in healthcare. I know a lot of people focuses on launch rockets and satellites, and while that's all fun and sexy, my focus is really not on that. And I put this as I guess a parallel analogy. Rockets and whatnot is basically like delivery trucks. Amazon, they don't make money by developing new delivery trucks. They just buy it off someone. What they focus on is the service they provide from delivering things. So if you put it into that context, what we should be focusing on is developing the services, the tools to be able to survive in space, or improve healthcare here on Earth. I think the rockets and all that is very well established. It's very mature. So if looking forward, I think there will be a shift towards more space services and providers of different types of space service. So I just want to introduce, obviously, my own company, Explore Space Technologies. And we develop a lot of different products and services, anything from food and drinks to health monitoring while you're up in space, and obviously monitoring your health when you come back to Earth. So these are the things that we want to work with the likes of Axiom to be able to do that health monitoring for those participants that goes into space. Apart from that, as I quickly mentioned before, we do develop performance suits. Our suit is going to be tested for ESA next year in Parabolic Flight. We do robotics. So our robotics is currently being tested for lunar missions. We've developed our own biological pharmaceutical CubeSat or Cube Labs for doing microgravity research. And of course, we have a suite of technologies for mental health in space, because that is also very important for long-term exposure mission in space. Obviously, I would like to acknowledge all my partners, global partners, because it's not possible for me to be able to do all this by myself and my team. And it really takes a village to raise a child. So I'm very grateful for all my partners, and this list has actually grown quite a bit already. And just something for you guys, because we haven't officially made a public announcement. It will be announced next week with NASA and CSA and Australian and Japan, is that we're going to be the first to go with iSpace to land on the moon next year, and also in 2023. So we're developing the rover technologies for doing certain missions on the moon. So we're very excited by this. So look out for the announcement next week. We'll be announcing that. So that's very, very exciting. And finally, I'd like to ask everyone, if you're interested in space biology and health, me and Rowena here tonight, we've put together our annual conference at asbx.com.au. It's completely free. We have a great lineup of people. Like I was telling everyone, that we have about 70 speakers so far, and they're all world leaders, and we have live discussion panels. So if you have any questions that you've always wanted to ask about specific topic, you can definitely do that. And of course, we also have a young researcher session. So if you are doing anything in this area, by all means, please submit your interest. So yeah, I think I kind of went over time, so sorry about that. Hopefully you found that interesting and inspirational.
All right, thank you so much for that, Joshua. Are there any questions that people have?
Yeah, don't be shy. I know everyone takes a while to absorb all this.
Okay, I'll ask the question. So I wanted to ask about the RPM you guys are working on, and then you're also going to integrate radiation with. Okay, it's just okay. I thought, but would you have to like use a separate room, like, because
yeah, so what we've done with the government agencies is that they have the radiation source, and we just place our RPM in the source, and they're able to do the research through there. So one of the biggest issue with radiation and electronics is whether it will fry up the electronics. So we were able to optimize it so it doesn't do that. So that's why I said it's probably the only one on the planet that has been demonstrated to survive. And we've been doing this research for almost a year now. So it's going pretty well.
Okay, I think Tianan, did you want to ask your question, even though it's quite similar?
Could you explain more about RPM method? Yes. So RPM method, like I said, it rotates basically everywhere. So based on the calculation of Airbus and also NASA, there's a certain rate, angle, and velocity at which it can rotate, in which that you can cancel out, or very close to canceling out, the effects of gravity. So it accelerates in X and Y. obviously don't quote me on this because I'm not a physicist, but the engineers have worked it out that you can reach that 10 to the minus 3 G. Like I said, microgravity is not zero gravity, it's just very low amounts of gravity. So 10 to the minus 3 G is almost identical to what you experience on the ISS. So that's kind of how the RPM work.
Vanessa, would you like to unmute yourself and ask your question?
Hi, my name's Vanessa. Nice to meet everyone. Just wanted to say thank you so much for the talk. It was really, really informative. I loved learning all about like the breast cancer stuff. That was so cool.
Oh, thank you.
And I was just wondering, you mentioned that you had like a cube lab, which was like a CubeSat that analyzes like pharmaceuticals in space. Is there anything else that you can tell us about that?
Yeah, so I mean, I'm not going to say that it's revolutionary or new, but because I've also done my own launches to the ISS, and right now in terms of what's available on the market, it's really, and I think that's also the problem with the RPM is that they were built by engineers to address a problem. They weren't built by engineers and biologists to cater for what we want. We have to adapt what we want to do with what's available. So, in terms of what is available right now on the market, it's very limited. What that means is if you think about a 1U, the maximum people can take up there is 6 samples. To be really honest and direct, 6 samples is not enough for anything that's even statistical. So what we have done is that create a fully autonomous system. It's very modular in that we can incorporate either organ on chips because that's very important to mimic different organ or systems in the body. And also our basic, I guess, cube can fit up to 20 samples. So you're going from 6 samples to 20 samples, which means you're getting more bang for your buck, so to speak, so that you can do more analysis and whatnot. And more importantly, it's fully autonomous because when you're trying to do experiments on the ISS, it's very difficult. The less you require the astronaut to do anything, the better. Getting them to press the on and off switch requires a lot of paperwork. So you can imagine if you're trying to get them to do complex biological experiments, it becomes very, very hard. So we're trying to make it as easy as possible. And because of privatization of space right now, I think in 2 years' time, we would not require to do these type of studies on the ISS. So we are talking with autonomous, I guess, space drones or spaceships that will fly even further than the ISS. And what we're working with them now is to use this technology so that you can conduct those biological experiments. But because these are autonomous, they're all drones, there is no issues about, is your thing going to explode and kill all the humans or whatnot. So it means that it can be streamlined and be more effective in terms of what we can do in space. So hopefully that answers your question.
Cool, thank you.
Tianan, did you want to unmute yourself to ask your question or?
Yeah.
Yeah, hi, Dr. Joshua, and hi, Dr. Chen. Thank you so much for the. I just want to ask more about the question to the Dr. Joshua about the random position machine, right? And also, I just to confused about that. What is the relationship between the random position machine, where just you have you, and also with the machinery? For example, what's the relationship between the machine learning now in using the AI and artificial intelligence technique and with the random position machine methods? And how can you talk me about that? What's the difference and what's the relationship between the raw methods how you to the microgravity and with the machinery? Yeah, Doctor.
I think I only caught 40% of that. I'm so sorry.
Yeah.
Do you just want to ask like straight questions? Like you don't have to elaborate, just Is that one question?
You can ask me one by one, and I'll answer them one by one.
Just one question about that. Can you make the difference between the methods, the random position machine and the machinery? Because can you tell me exactly about that? What's the difference? And the second question about that, what is the relationship between the random position machine with the machinery?
Sorry, Yinkai, did you get that?
Two question, yeah. It means that can you tell me about that? What's the difference between the random position machine and the machinery?
And machinery?
Right. The machinery, for example, in the artificial intelligence, AI or neural network, for example.
I hope I understood that. So you're asking me what's the difference between RPM and AI?
AI, right? Yeah.
Oh, I think that's very, very different, because AI, you're talking about software, and RPM is a physical machine. So it is very, very different. But having said that, you can apply the principles of AI to analyze the data from RPMs. But in terms of difference, you're talking about software and hardware. So yeah, it is very different.
Just different. Because just the random position machine have been collected, right? When they collect to all the objects in the space, and also how to use, for example, how can you use the software? What is software? How to use in the random position machine?
Okay, yeah. So, sorry. Okay. So the software, yes. So the random position machine, it is driven by software. And those software we have written ourselves. So we have developed them ourselves. So yeah. So the software is developed in accordance to what is published out there, what is accepted, and that's why I said what Airbus has used and what NASA has used. So those are numbers and mathematics and physics calculations that they have done to demonstrate and prove that you can get 10 to the minus 3 g at this certain speed, certain angle, and certain velocity. But that is just like any other machine that has a software that drives it.
Yeah, because that's, this method has used a machine. Just you need to software actually. So just what is the method to actualize the software, right? And also to using the random position machine.
Yeah. No, yeah, it's definitely driven by software, but that software is set because it runs at a specific, like I said, speed, angle, and velocity. So that is all set. But in terms of our machine, we have the capability of letting people change those parameters if they want to.
Thank you, Joshua. Yeah, thank you so much.
No worries. Hopefully that answers your question.
Okay.
Yeah, thank you. Yeah.
All right. Bernard, did you want to unmute yourself and ask your question?
Yeah, thanks, Yankai. Hi, Dr. Joshua and everybody. I'm really pleased to meet you all. I'm Bernard. I'm actually a researcher with the Philippine Science Department, specifically under the Philippine Nuclear Research Institute. We conduct radiation biological research with our X-ray irradiators here in our lab. Your presentation was really interesting to me for obvious reasons, and I wanted to ask a bit more on the details with the irradiator that you used for your RPM. Like, did you use like a gamma irradiator, a particle accelerator for proton, perhaps iron 56 to simulate high atomic weight particles? Because these are the hazards in space, the long-term hazard in space.
The one I can tell you is the gamma. That part I can tell you that we have done things with gamma. The more exotic ones, those are being done, but I don't think I can share too much about that because they're in certain government facilities. Yeah, it's a little bit sensitive. But in terms of our general, in terms of what my student does, we have gamma X-ray sources. Yeah.
Okay, because in the future, I think it's possible to use a conjunction of RPM and irradiator so that we can investigate more on the effects of both of these things to different parameters, whether that's in vitro or in vivo, no?
Yeah, absolutely. And yeah, like I said, my biggest concern was that frying the chips or the motors on the RPM than anything else. So far, no one has presented to us with a dead machine. So I presume that is still functioning. But yes, like you said, those are very important and valid questions because you can't have one without the other. So that's why we started 2 years ago to have those discussions, establish this facility to be able to do both and to really answer those underlying questions.
Awesome. I do have one more question. You mentioned a while ago on microgravity and the blood-brain barrier and the chemotherapeutic drugs. Has there been studies that investigate the effect of microgravity with regards to drug absorption or bioavailability of these drugs?
I want to say there is people who have done that, but I guess it depends on what context. If you're talking about GBM in terms of brain cancer specifically, then the answer is no, not that I'm aware of. But uptakes of drug and drug, what do you call it? I guess drug dissociation, those are things we're doing right now. Because, as some of you will know, for example, Panadol, when you take it to space, it affects it and it doesn't really work. So there is actually no painkillers while you're in space. And of course now, there are space agencies who are looking at 3D printing drugs. So we are working with those entities to look at, how those 3D printed drugs will fare in space under microgravity. Would it also dissociate? And similarly, you can also appreciate, having that dual function of microgravity and radiation, what happens to these drug compounds. So we spent the last 6 months setting that kind of process and experiment up. So we're working on that right now. But it is more on drugs in general, but not so much specifically on uptake by certain cells. But I think that's why this is really interesting, because there's so many unanswered questions because no one has really looked at it this way. So that's why we developed the RPM so that more people can be able to use it. And one of the limiting factors with the Airbus one was it's ultra expensive. Our price is about 1/6 or 1/10 of the price, so that everyone can do more. So literally this week we're talking to partners and really to enter the US market and getting our RPM as part of the NASA pre-flight testing workflow, because how do you de-risk your experiments when you're trying to do it on the ISS? You cannot possibly go up and go, oh, okay, sorry, that cell number did not work out. Let's do it again 2 years later and $500,000 later. So we are trying to build a global community to be able to answer some of those what is very basic questions that we don't have answers to.
Awesome. Thank you, Doctor.
Christine, would you like to unmute yourself?
Hi, I'm Christine. I'm also from the Philippines. I'm just curious about how hard is it to do experiments or propose experiments in the ISS? I mean, who do you contact for that, or who do you propose to that? Is that the national agencies or some entity?
No, those are very good questions, and this is something we want to help researchers demystify is what is that process. So there are a lot of private launch providers. There's about 4 or 5 in the US, like Space Tango, NanoRacks, and so on. I work with Yuri Microgravity from Germany, so they work directly with NASA as well. There are also companies in Japan that I also partner with. So there is a lot of private providers that can help you design and facilitate space launches and experiments on the ISS. Hopefully that answered your question.
Yeah. Thank you, Doctor.
No worries.
Are there any more questions? Or okay, all right. I think I will call it off now. Otherwise, I want to thank Joshua for giving us such a wonderful talk and answering many of our questions.
Thank you.
Otherwise,